So our next speaker is Ilan Rosen from MIT, and he's going to be telling us about a synthetic vector potential on a superconducting processor. So please take it away.
Great, thanks for the introduction, and thank you to the organizers. Mic's okay, coming through? Great. All right, so yeah, I want to talk to you about some of our recent work. We've been running, Bose-Hubbard type simulations for a while on these types of superconducting devices, but we wanted to add some more ingredients, and in particular, I'll show you that we can add something that looks a lot like a magnetic field, and then we can, try to use this capability and do some fun physics at the end. So let's just jump in and start with the device. So this is an image of our device. It's a 4x4 array of transmon superconducting qubits. Adjacent qubits, nearest neighbors, are capacitively coupled. This is just the qubits. To actually run these chips, we actually have this whole other chip of resonators and control lines and everything. We bring these chips together in a flip chip geometry, so we can actually do these experiments. This is kind of standard now. But I do want to thank Sarah Mushinsky, a grad student in our lab, who designed this device, and also Lincoln Laboratory, where this device was fabricated. Okay, so what does this do? So if we just write down the Hamiltonian of this device, no tricks, just straight up, it just is a Bose-Hubbard model. It has some on-site energy that's tunable. It has some coupling that's fixed on this particular chip, but it's a nearest neighbor hopping type interaction. And then it has some anharmonicity. Anharmonicity says there's an extra energy cost to having two excitations on one site. It turns out that for regular transmon qubits, that energy cost is so big compared to other energy scales in the system that we can basically just forget about it. We can say, having two excitations on a site is so costly, let's just throw that out of the system. And then we can project onto what we call like the hardcore Bose-Hubbard Hamiltonian, where we're treating every site like a Pauli operator. It can either be occupied or unoccupied. I do want to point out that it's still bosonic. It still has bosonic statistics. Good. Okay, so this works. Our group's been doing it for a while for quantum simulations. There's a lot of other groups doing it. Chicago, Stanford, Princeton, you heard from Tron to Google this morning, ZJU, CAS. Okay, so this works, it's great. There's kind of just like one little problem, which is, if you're like me, you're coming from a condensed matter background. We don't really have condensed matter systems that look that much like a Bose-Hubbard model on a square lattice. There's a lot of other models that I think are kind of closer to what we study in condensed matter. So that's kind of the jumping point for this work. Can we take these devices and use all their power and simulation ability, but make their Hamiltonians look a little bit more like something that you'd actually maybe measure in a condensed matter lab? So if you go to a condensed matter lab, as many of you probably have, you've probably seen something like this. It's a big dilution refrigerator, big cylindrical can, and inside there's probably a superconducting electromagnet, right, to get 6 or 9 or whatever, 14 Tesla of magnetic field. So these magnets are ubiquitous, and there's a really good reason for it. A lot of interesting states rely on having magnetic fields. A lot of topological states, like the quantum Hall effect, you need a big magnetic field. But also, if you just want to characterize condensed matter materials, it's really helpful to have a magnetic field. You can check properties about the carriers, things like the coherence length. You can look at interesting phenomena, symmetry breaking phenomena like magnetism. Right. So if we want to do these quantum simulations, I think, to me, it makes a lot of sense that we want to build in the magnetic field. There's like a little trick to this, though, which is that we're using superconducting qubits. And not only do superconducting qubits really not like magnetic field, but if you did put on a magnetic field, the particles here are photons. So they really wouldn't care. Their dynamics wouldn't be affected. You just destroy the chip. So we're going to have to be a little bit more clever if we want a magnetic field. So let's jump back to basic physics. So we want to emulate something that looks like a magnetic vector potential, right? Like this A, right? Now, if we map this continuum model onto a lattice, this is done by something called a Pyro Substitution. These vector potentials A map onto a complex phase on the nearest neighbor hopping terms, okay? And if we can realize something like this, then we can use these phases just like we'd use a vector potential, right? So, Gauss's law for magnetism should hold if we have some spatial gradient of these phases, so that if we, take the phases in a loop and sum them up over all these bonds, then the overall sum of the phases corresponds to a magnetic flux threading that loop. Okay, so Gauss's law for magnetism should work. And we can also think of Faraday's law of induction, right? So if we start taking time variation of these phases, then we should get an electric field, or a synthetic electric field. Okay, so this gives us a recipe to realize a synthetic electromagnetic vector potential in a superconducting processor. We just have to figure out how to do it. It's a little tricky because, normally we just let the qubits talk to each other on resonance. They have this intrinsic swap interaction or hopping interaction. That turns out to be real. The coefficient for that is real, so it doesn't have this vector potential built in. But what we've found is if you go to a different coupling scheme where you actually intentionally detune the qubits and then you modulate one of the qubits at that detuning frequency, it turns out that the phase of that modulation term is directly the complex phase of that hopping interaction. Okay, so now we just have a recipe to do it. So we went ahead and extended this parametric coupling protocol over the whole lattice. So we have to choose a whole bunch of DC frequencies. We have to choose corresponding modulation tones. That corresponds to activating all these nearest neighbor bonds. And then we have to apply some phases to get the right vector potential. Don't worry about the details here. That's not the point. I do want to just point out a couple things. So first of all, here we're modulating. We have 16 qubits that we can modulate. We have 24 nearest neighbor bonds in a 4x4 array. But it's okay. It turns out that if we're clever about choosing all these parameters, we actually do get full control over the magnetic field. So we can either make a uniform field or we can choose the exact flux through each plaquette. And we similarly have a lot of control over the synthetic electric field. And so if we put all this together, what we have, bottom line, at the end of the day, is the Harper-Hofstadter model. And in short, this is like the conventional model for a magnetic field in a lattice. It's what you use if you're, say, doing quantum Hall effect. You want a lattice model. This would be your go-to. Okay. So let's check and see if this works. So first, let's go ahead and take a loop of, in this case, 12 qubits arbitrarily. And let's put a phase on one of these bonds. And so again, if we sum up the phases around, we should have a net flux threading the plaquette. And so we see something really cool. We see that at zero flux, here I'm showing you initialization of a particle at one end, and I'm showing you readout, so the population at the opposite side of the ring, highlighted sort of in orange. So we see something really cool. We see that at zero flux, the particle will get to this opposite side. It'll go back. It'll oscillate back and forth. Okay, and then at pi flux down here, we see something really different. We see that the particle never gets there. Okay, so this is Aronoff-Bohm interference, right? So we're showing the destructive interference of propagation of this particle across the ring at pi flux. We're showing constructive interference at zero flux, and in between there's this really complicated interference pattern, and that just has to do with this being a ballistic quantum particle, so it's kind of interfering with itself as it propagates around this ring. Okay. So on the right here, I'm showing you a full simulation of the experiment. On the left is the actual experimental data. And I just want to point out that, any differences between these plots are essentially the experiment not being exactly right. So we're simulating this to the best of our ability, but maybe there's some miscalibration or whatever. But I'm also going to show you a second theory plot, which is of the very ideal Harper-Hofstadter model. And there are some differences between the Hamiltonian we realize and the ideal Harper-Hofstadter Hamiltonian. There's some extra rotating terms. And there's also some coupling strength disorder just baked into the chip that, all the qubits don't quite couple at the same rate. So we've done our best to mitigate these effects, but they're still present, so there are some differences. But the key is that the patterns are all the same, right? The interference pattern in general has the same dynamic. So qualitatively, we're getting the right physics. And throughout this talk, I'm going to keep showing you kind of these two layers of simulation. Okay. So bottom line, we have Gauss's law for magnetism. We can make synthetic magnetic fields on the chip. Let's do the same thing for electric field. So here, I'm going to use the sort of perimeter of the chip as a 1D chain with open boundary conditions, and that's just to make this easier to see. And then let's time vary all these modulation phases so we get a uniform effective or synthetic electric field across this chain. Now, when that electric field is 0, if we launch a particle at the middle of this chain, it's just going to propagate to the boundary, bounce off, and keep bouncing back and forth, interfering with itself, making some funny pattern. Okay, but let's try turning on the electric field. Something really different happens. So here the particle stays really tightly confined to the initial site. The larger this electric field, synthetic electric field, the tighter the confinement. And maybe this is a little confusing because we're used to kind of free space, where if you turn an electric field on, a particle wants to accelerate in one direction. That's not the case for a ballistic quantum mechanical particle in a lattice. We actually expect this type of localization, and it comes from block oscillations. So there's a few different ways to think about it. If you want a momentum space picture, it's basically the like wave vectors kind of rapidly oscillating around the Brillouin zone, and at the end the particle can't actually move. Okay, great. So this verifies that we have as well a synthetic electric field from this protocol. So now we get to do some fun physics with it. So let's start by thinking about the Hall effect. So we can turn on a uniform electromagnetic field across this whole 4x4 array. And I've sort of tilted the lattice here, so we can think of the horizontal as being the x-axis, vertical as being the y-axis. I'll have an electric field along the x-axis. I'll have a magnetic field out of plane, so like z-axis. And then if the Hall effect works, we should see deflection of the particle up or down accordingly. So first I want to show you, just for some random magnetic field value, I want to show you the position, the x-coordinate, so the longitudinal coordinate of the particle as a function of time. So since we're starting at one end, the particle is just going to be launched. It's going to travel across the lattice. So after, unit 2.5 or 3 or something in units of the coupling strength, it gets to the other side. Great. And I want to point out that this happens kind of regardless of the electric field, right? Because I've initialized the particle on one side. So as long as the electric field isn't super strong, it always just goes, in this case, to the right. Okay. So what do we expect would happen? We're thinking about a classical Lorentz force. We would say we have an x velocity, right? And we have a z magnetic field. So we should always have, in this case, a negative y force. So the particle should always go down, right? Well, let's look at the data. It's not at all what happens. So something really different happens. If the electric field is, in this case, negative, the particle goes down. If the electric field is positive, the particle goes up. So okay, what is going on? This is really weird. It turns out this is actually what you should expect for a ballistic particle in a lattice. So we can actually model this really nicely, semi-classically. I apologize for rotating the axes here by 45 degrees. I do that to make the plots look nice. But let's actually look inside the Brillouin zone in a semi-classical momentum space picture. So the colors here correspond, again, across the kx, ky Brillouin zone to the transverse velocity. So there's this really interesting double mirror symmetry. And if we take this initial position of the particle, we put it into momentum space, it has this kind of contour. I'm just giving you a cartoon with this black ring. But it has this really nice symmetry in the lattice. And if we watch how this contour evolves in the lattice under an electric field, it kind of stays along one of these mirror axis symmetries. And if it evolves only in a magnetic field, it stays along the other mirror axis symmetry. And so to get a net transverse velocity, we actually have to have both an electric and a magnetic field. And the signs of both determine sort of which quadrant and therefore which sign of transverse velocity we'll end up with. So this is a little bit counterintuitive, but it turns out this is really what you should expect, again, for a ballistic quantum particle in a lattice. It's very different than the free space or dissipative Hall effect picture, which is what we're more used to in condensed matter. So here's some data to just kind of summarize all of this. What I'm showing you here is the time averaged transverse coordinate of the particle. So this is just kind of one metric to show you how far the particle goes up or down. And I'm showing you a whole bunch of different magnetic fields and electric fields. And you see there's this very beautiful symmetry where the sign of the deflection depends on both the sign of the electric and the sign of the magnetic field. I also want to point out that there's this kind of skew in the data. If you compare the like ideal simulation to the experimental data, everything's kind of skewed, and there's also a very beautiful symmetry argument for that. It's because there's built-in disorder. There's coupling strength disorder in the lattice, and that breaks the same symmetry, spatial inversion, as the electric field, but not time reversal, which is what the magnetic field gets you. And so it looks like there's kind of a built-in electric field, but not a built-in magnetic field. Okay, so again, we're seeing these really like beautiful reflections of the particulate symmetries of the Hall effect in this lattice. Cool. And then really quick, we can also look at some differential quantities, come up with some metrics, and these are kind of metrics we can compare to what you'd actually measure with a lock-in if you did this in a real material, like Hall resistance or Hall voltage or whatever. Okay. So to wrap up, I want to tell you about kind of a newer experiment that we're working on now, which is to look at flat bands. So if we use the middle 3 diagonals of this lattice, we form 3 unit cells of what's called the rhombic lattice. And this is a really interesting lattice because depending on the flux through each plaquette, we can tune between a regime where the bands are dispersive or at pi flux where the bands are all flat. And this is really special. All 3 bands are flat. I think many of you have heard about recent advances in twisted, magic angle twisted bilayer graphene. The idea here, and in some other materials as well, is to get flat bands, quenches kinetic energy, and there's really incredible physics that happens as a result. The same thing happens in the rhombic lattice, but because all 3 bands are flat now, every single eigenstate should be geometrically frustrated and therefore localized at pi flux, and that's really special. So let's do the same kind of quantum random walk experiments. We'll start with a particle at one end, we'll let it bounce around, and we'll see how far it goes as a function of time and magnetic flux. And again, at 0 flux, you see that it starts on the left side, and it goes all the way to the right side and back and forth. Great, it's a propagating particle. And as we tune towards pi flux, we see something very different. The particle is intrinsically localized, so it stays completely within the first unit cell at pi flux. And again, that's just a consequence of flat bands. We can just summarize by making up some statistical metrics for this. Here's position moment. Here's a localization length we can extract. It's not important. The idea is basically low values mean the particle's localized, high values mean the particle's conductive. So this is the equivalent of a conductivity measurement you'd make with a real material. Okay. Great. So we've shown that there's localization physics intrinsically at half flux. Cool. Let's add disorder. So if we do this, I'm showing you data, again, both of these 2 metrics. High values mean conductive, low values means localized. And I'm showing you 10 random disorder instantiations at different strengths. And then the kind of darker markers indicate the average, disorder average value. So that's kind of what we would think of as being equivalent to like a condensed matter type measurement. Okay. So at 0 flux, we see exactly what we'd expect. We see Anderson localization, right? So as we ramp up the disorder, we see more and more and more localization, right? Great. See something totally different at pi flux. We see disorder-induced delocalization, right? Which is really bizarre. As we turn on the disorder, we're actually destroying this flat band localization, and we're allowing the particle to propagate with increasing disorder. And that works for a while. Eventually, like Anderson localization takes back over at really high disorder strengths. But this is really cool physics. So the bottom line is we're using this ability to have synthetic magnetic vector potentials to explore interesting condensed matter systems, but with this degree of tunability that, at least in my opinion, is really unavailable in natural materials. So this, artificial material gets us that. So yeah, to conclude, we have this, superconducting analog emulator. We've added this new ingredient, the synthetic magnetic vector potential, and then we can do a lot of fun physics with it. I want to thank my group. There's, a lot of people that make this happen, both MIT, Lincoln Laboratories, and I also want to highlight a couple theoretical collaborators, Arko and Michael, at MIT. Great, so with that, let me leave up QR codes in case you do want to check out these papers. The stuff about the rhombic lattice will be coming out sometime this fall, and thank you very much for your attention.
Thank you very much for the talk. So questions?
Yeah, thanks for a nice talk. I had a question about the rhombic lattice. So you show this disorder-induced delocalization, which is very cool. I think there's also a prediction that if you have like 2 particles interacting, that can cause delocalization. So is that something you could do or have looked at?
That's a great question. I don't think I have the data with me on this slide deck, but that's absolutely something we did, and it's exactly like you said. Multiple particles, the interaction between them destroys that geometric interference, and then you get propagation again. It's a great question.
Other questions?
Yes, thanks. I'm just curious, like, if you have any comment on the effect of decoherence in the device, and how does that compare with like disorder? Like, basically, how easy or how hard it is to calibrate the system? Like, yeah.
That's a great question. Yeah, so our initial thought was that some of these differences I mentioned. Let's go back to the data. My initial thought was, that some of the differences between theory and experiment were due to decoherence. But when we analyze that more carefully, it actually looks like decoherence doesn't do much. So in lab units, this experiment lasted 1.2 microseconds. The coherence times are, depending on if you're thinking T1 or T2 or whatever, are more like 5 to 20 microseconds. And it turns out just not to do much in that time span. Miscalibration error also does something. So we can only basically guess the qubit lab frequencies to about 200 kilohertz. Beyond that, it's pretty hard to, and they also drift a little bit. So yeah, I was expecting that to matter a lot because, again, the coupling is 2 megahertz. And so if we can tune up to 2 kilohertz, that's like a 1 part in 10 calibration error. Again, it turned out not to matter that much. And the biggest effect is just these extra rotating terms from all these modulation tones, which kind of interfere with each other. Yeah, good question. Thank you.
Right. So I think we have to move on, but let's thank Ilan again.